Hello everyone, let's talk about integrating factors. So integrating factor is the standard technique for solving the first order differential equations of the form dy dx plus p of x times y equal to q of x. For y is the dependent variable and x is the independent variable, where p of x and q of x are the functions that depend only on x. To solve for the solution to these differential equations, you need to follow a certain procedure. The first step is to identify and solve the integrating factor, and I call this mu of x. For mu of x equal to the exponential functions e to the power integral of p of x dx. So this is necessary for you to correctly identify the representation of the function p of x. After you solve the integrating factor mu of x, you multiply both sides of the equations by the integrating factor. That is mu of x times dy dx plus mu of x times p of x times y equal to mu of x times q of x. If you look at the left-hand side more closely, you will be able to identify this is derived from the product rule of d dx of mu of x times y, and the left-hand side stays the same, mu of x times q of x. If you are not sure why the left-hand side is derived from the product rule of derivative of mu of x times y, then let's work out the detail together. You know that the integrating factor mu of x equal to e to the power integral of p of x dx. So that is, you have d dx of e to the power integral of px dx times y. Now apply the product rule. So that means the derivative of the first term times the second term plus the first term times the derivative of the second term. We have d dx of e to the integral of p of x dx times y plus e to the integral of p of x dx times dy dx. Using chain rule for this term, you will arrive at e to the power integral of p of x dx times p of x times y plus e to the integral of p of x dx times dy dx. And once again, e to the power integral of p of x dx is mu of x, which is the integrating factor. So I just show you that the left-hand side is in fact coming from the product rule of mu of x times y. Now let's move on to the next step of the procedure to solve the solution of the first order differential equations using the integrating factor. In step 3, you need to integrate both sides of the equations with respect to x. In step 3, you need to integrate both sides of these equations with respect to x. That is the integral of d dx of mu of x times y dx equal to the integral of mu of x q of x dx. For the left-hand side, if you use the fundamental theorem of calculus part 1, you will obtain mu of x times y equal to the integral of mu of x times q of x dx. And to obtain the solutions to differential equations, you can divide both sides for the integrating factor mu of x. You can get y equal to 1 over mu of x times the indefinite integral of mu of x times q of x dx. So this is basically the procedure to solve the solution to the first order differential equation using the integrating factor. Let's recap the procedure one more time. First, you need to identify and solve the integrating factor mu of x. Next, you can multiply both sides of the differential equations by the integrating factor. And remember, the left-hand side is always derived from the product rule. That is, you have d dx of mu of x times y equal to mu of x times q of x. The third step is to integrate both sides of that equations with respect to x. Using the fundamental theorem of calculus part 1, you can obtain the left-hand side as mu of x times y. On the other side, the indefinite integral of mu of x times q of x dx can be evaluated using integration techniques that you know before, such as basic antiderivative formula, integration by substitution, integration by parts, or integration by partial fraction decomposition. And to get the solution to the differential equation, you can now divide both sides for the integrating factor mu of x. Now let's apply this procedure into a couple of examples. In this example, I would like to use the integrating factor technique to solve the following initial value problem. The differential equation is dy dx plus y equal to x. This differential equation is subjected to the initial conditions y of 0 equal to 2. So the first thing that you need to do when using the integrating factor is to identify p of x. So in this case, you can see that p of x is equal to 1 because 1 times y is equal to y. So p of x is equal to 1. Now let's follow the procedures that we have earlier. So first step, try to evaluate the integrating factor. So that is mu of x equal to e to the power integral of 1 times dx. The antiderivative of 1 is just x. So the integrating factor is e to the x. Next, you need to multiply both sides of the differential equation by e to the x. That is e to the x times dy dx plus e to the x times y equal to e to the x times x. And remember, when we discussed about the procedure, the left-hand side is always derived from the product rule of the integrating factor times y. So that is d dx of e to the x times y, because the integrating factor in this case is e to the x. And the right-hand side stays the same, that is e to the x times x. Now, third step, you need to integrate both sides of the equations that you just obtained with respect to x. So that is the integral of d dx of e to the x times y dx equal to the integral of e to the x times x dx. We know that from the procedure, if we apply the fundamental theorem of calculus part 1, you can rewrite the left-hand side as e to the x times y equal to the integral of e to the x times x dx. Now the last step is to find the solution to the differential equations. Right? To do that, you have to evaluate the indefinite integral on the right, e to the x times x dx. To evaluate the integral, you need to apply integration by parts. So that is, you let u equal to x, then du equal to dx, and the dv part is equal to e to the x dx. This gives me v equal to e to the x. So therefore, the equation becomes e to the x times y equal to x times e to the x minus the integral of e to the x dx. Now, the integral on the right-hand side is very straightforward. The antiderivative of e to the x is just e to the x. So now we arrive at e to the x times y equal to x times e to the x minus e to the x plus a constant c. To obtain the solution, you can divide both sides of the equations by e to the x. So that is y equal to 1 over e to the x times e to the x minus e to the x plus the constant c. You can simplify the solution a little bit further by distributing 1 over e to the x into the parentheses to get y equal to x minus 1 plus a constant c divided by e to the x. So e to the x is in the denominator, but I want to bring that into the numerator. When I do that, I will change the sign of the exponent, that is e to the negative x. So this is the general solution to the differential equations. Now you can utilize the initial conditions to find the value of c. So utilize the initial conditions, y of 0 equal to 2. That is the input value x equal to 0 and the output value y equal to 2. So I get 2 equal to 0 minus 1 plus the constant c times e to the 0. Right. You know that e to the 0 is equal to 1, so the solution for c is 3. Now from here you can write down the particular solution as y equal to x minus 1 plus 3 times e to the negative x. So the example is done. We just use the integrating factor to solve the solutions to the initial value problem.